This is the solution video for the multiple choice. For this one, what is the possible outcome? So the keyword is here is possible. Outcome for a moving object with a net force of 0 newtons. So this question is asking you, of course, about translational equilibrium when all the forces cancel out, and there are a couple things that have to be true if a thing is in translational equilibrium. One thing is that it cannot accelerate. So anything that has to do with accelerating has to all just automatically be canceled out. So this one has an object must be accelerating. That can't be that one. The object is moving with a constant speed. That has to be true because, like we just said, it's not accelerating. So I would check that box. The object is slowing down. Again, slowing down is a changing velocity, so that's accelerating. That one cannot be true. And the object must have forces on it, have a force on it, and that actually doesn't have to be true. Let me draw a object that is in translational equilibrium that doesn't have a force on it. This right here. There's a box. There's no forces. It doesn't mean that there isn't a velocity. Of course, there would have had to be a force on it for it to get moving, but you can, like, for example, if you throw a ball in outer space and we're in deep space, there wouldn't be any forces on it because gravity's not pulling on it. There's not any air in outer space to cause air resistance. So we would get a velocity. Let's say we threw it to the right. We get a velocity to the right, but there would be no forces, F net, and not even F net, but all the forces, it's equal to 0. And so that is an example um, of where this one isn't always true. So the only thing we should check on this one is the object is moving with a constant speed. For number 2, this one is about an elevator, and it's asking which one would be accelerating the most. And the key here is just simply to look at the net force. So I have an option on here that you don't necessarily have, but I'm just going to draw an arrow right over the top of W so you can see the addition of the two vectors here. So you're looking at the tug-of-war battle. So if you look at the T and the W, you're looking to see the net forces. How much is the W canceling out the T? And so one easy way to do that is, you don't have this luxury, but I'm going to put the vectors together like this, and you can see that this object right here has a net force of that much. Okay, so I'm going to just do that for all of these. This one we don't really have to do anything for. You can see that the W and the T are almost going to cancel out. So let's take this right here, and we do this, and so it's got a net force. Oh, this one should be up. Sorry, this one is down. If we go back here, the net force should be up that much. This one here totally cancels out. T is just as big as W. And so the one that would be accelerating the most would be D. So we'd want to select D for this. And that's just having to do with, well, you take your force vectors and you add them together. Well, there's not anything other than just the W, so that is the addition. And as you can see, the net force here is going to be just the length of W. So if you take a look, this one has a net force of 0. This one has a little net force up. This one has a little net force down. D has the biggest net force, therefore it will accelerate the most. And we got one more here. A free body diagram represents the forces on a textbook. So these are all should be representing forces on a textbook. Which would be the best description of a textbook? Well, let's talk about what we did in the last problem with the one where the net force is down and only down. Like C would represent something falling or breaking through the desk, I guess. So C can't be true because it's resting on the desk. D, again, this one has a bigger net force down. If you look at N and W, there is a bigger W than there is an N. So we're going to get a net force down. So that would be accelerating through the desk. That can't be true. So we're stuck between A and B, and this is what a lot of people do. A lot of people like to fill up all the dimensions for this problem for some reason. So they automatically are gravitated for some reason towards this one because you have some sideways forces. But if the object is just resting on a text on the table and nothing is pushing it, there doesn't need to be those sideways forces. So I'm just going to remove those. This situation, in the problem, it's not what it's asking for. It's resting on the desk. They don't say anything about anybody pushing on it or friction on it or anything. So it should be B is the correct answer here. The key as to if you wanted to see why, W is just as long as N. So your net force here, F net, would be 0. And that's key because the reason why your net force has to be 0 is, well, your object is at rest on the desk, so it can't be accelerating. So you need a net force of 0 there. I hope that was helpful. Those were the solution videos.